The chair of the session is Laurent Amsalek. And so
Hello, everyone. It's my real pleasure to begin this very special edition of SISAP with Marcel Worring, who is going to give the first keynote. So before Marcel starts, I would like to say a few things about him. And unfortunately, my camera, for some mysterious reason, is just not working. So you cannot enjoy my beautiful face. That's okay. So Marcel is a full professor at the University of Amsterdam. Some of his scientific motivation come from his desire to develop methods for accessing large image and video collection by their content. And this obviously means that Marcel had to contribute to techniques facilitating the analysis and understanding of visual material. In addition, however, Marcel always believed that user interaction is crucial in order to get insight about what contains a large collection of multimedia material. And that this interaction is in fact an interplay between advanced visualization of the collection, of query results, and also of what the user is exposed to through browsing and navigation. And all this goes far beyond classical data visualization contributions. And it grew up to the point that an entire field has been unlocked. This field is called multimedia analytics, and this is the integration of multimedia analysis, multimedia mining, information visualization, and multimedia interactions. And over the years, applications areas are semantic video search engines, forensics, and also cultural heritage. But I want to say a few more words about Marcel. Marcel has a very impressive publication record, and he has also a lot of dedications to the community by being involved as an associate editor of many multimedia-related journals. And Marcel played a very central role in various top-level conferences in multimedia. He was the general chair of ACM Multimedia 2016 in Amsterdam. And I think you are the program coordinator of the 2020 edition of ACM Multimedia, Marcel. And by the way,
yes,
you know this.
I am.
You are, yeah. By the way, this edition is also special. It's going to be virtual. So go and check the web pages of the 2020 edition. Then the registration fees are extremely small. And because of the virtual environment, it's going to be a great opportunity to know what is going on inside that conference. So Marcel, you give the first keynote of this edition. This keynote is about interactive exploration using Hypergraph. And so I am absolutely convinced that we're going to hear things that are topics that are central to the SISAP crowd. Notion of similarity is going to be in your talk for sure. The need to work with sophisticated metrics to do metric learning. The never-ending combat against the curse of dimensionality. The usefulness of features, and also as demonstrated by various talks in the previous editions of SISAP, the incredible power of graphs. And all this involves difficult problems in relation with interactivity and the underlying support for dynamicity, and that's complicated. And because of deep learning, which is everywhere these days, and the incredible efficiency and the large diversity of convolutional-based networks, all these calls to revisit some of these notions that are central to SISAP people. And at the same time, it leads to new opportunity when analyzing large multimedia collections. And this keynote is thus very close to the heart of what we are all concerned about in SISAP. Marcel, the floor is yours. Go ahead.
Well, thank you for the introduction, and thank you all for being here. Very happy to talk to you today. So, yes. So you talk about similarity in many ways. When I talk about similarity, I always think in terms of multimedia, because multimedia now is really everywhere. So if you look at Facebook, most of the content there is image data. If you look at Instagram, that is basically only geared towards visual data with text as a little complement to it. everybody, of course, is using Netflix or other kind of platforms where they really need to make a recommendation based on the content of what is in there. Online shopping, a combination of images of the products that are there, reviews from people which are text, people that give stars, recommendations, all things where multiple channels of information are connected and are bringing you the full experience where you go really beyond just one channel. And of course, TripAdvisor, although we cannot be there, TripAdvisor can help you in showing what is there in Copenhagen. So Björn, I will take your invitation and at some point we'll visit you. So if you talk about multimedia, there we have to think about how to represent the multimedia. And multimedia has a number of components that are relevant when we do analysis. So of course we first have the content itself, so just the images, the videos, the pieces of text, and we have annotations of this data. And this annotation can be just given by users, so added in the form of tags or other kind of things or other labels, or it can be what the system is automatically deriving as potential descriptions of these multimedia items. And in addition to that, all the kind of applications that we are talking about, all the kind of social networks, there is a lot of information available as metadata. Where are pictures taken? When are pictures taken? By whom is the picture taken? All those kind of related information, which is not directly part of the content, but it does give a very important description of what is actually there in the content. So those are the individual components. And from these components, we can, from this part, from the content and from its annotations, we can derive features. We can all make all kind of measurements, or at least compute all kind of features. And we can post statistics on top of that, and that's the statistics on which you can do all kind of different processing. But there are also two forms of similarity that play a role here. So there is the perceived similarity between items. So when do we feel that two items are the same or far apart from each other? And of course, based on the features, based on the metadata, based on the content, we can derive similarity features between the items from the system point of view. And of course, the challenge is how do we bring those things together in one system? And we have been looking at analyzing multimedia data and exploring it for a long time already. And as Laurent said, we always look from how you're going to use the data. So how do you give access to those large collections of material? And a while ago, in 2014, we came up with the so-called search exploration axis, where we said, well, there's a kind of search part where you have tasks like ranking your data or finding some very specific elements in this large pile of information that you have, or more like you do in a search engine, just find relevant items belonging to some of the categories that are important. Can you make a summary of the data? Can you add structure to the data? So can you identify interesting groups? Can you identify connections between them? And can you start browsing just which you don't know where you're looking for, but you want to find some interesting information? Well, this is where really the exploration part is coming in. And if you look at how we search through data, you basically have a clear idea of what to look for. So you can pose a query term in your search box, and from there you start looking. The focus is really getting on specific results. You typically pose one, maybe two or three queries, but you're not taking a long time. And the model of the data that you have is static, so that it doesn't change. So it's easy to use indexing structures on this part if you're doing search. Well, if you move to exploration, things are quite different. Because if you start exploring, if you start browsing for data, if a user, you have to support a user in doing that, it's unclear what this user is actually looking for. So what are the elements that play a role? That's very hard to determine. And the user itself, especially if it is an expert user, it's just focusing on discovering interesting items and finding interesting items to look at. And typically, if you are in the exploration phase, if you have exploration systems, you're focusing more on discovery. You have long interactive sessions. So you really start interacting with your system. It also means that you need better visualizations and more tools for the user to do interaction. And very important in comparison what we have here, you basically have a dynamic model of the data. So the data might actually change, or the model of the data that you have might change based on the interactions that the user is having with your data. And that makes indexing and all those kind of elements very different from what we have here. And now if you look at what happened over the last 10, almost 15 years, mostly 10 years, when deep learning came in, you see that for those kind of tasks, so taking an image and being able to recognize that there's a person, a dog, and a chair in this picture, in 2010, that was a very difficult task where the errors were high. It's now, you can't see it, but about 25% in the task that is corresponding to this. But then deep learning came, basically starting with the AlexNet on the ImageNet data, and performance was improving dramatically. Well, in 2015, ResNet 152 came out, one of the most advanced deep learning systems, and they really dropped to a very low number, only 3% of error. And in the 2 years after, they went to only 3% and 2%. And this is actually very close to the human performance on those kind of data sets, because it does, those data sets also contain images of very specific dogs and other very specific animals, which are very difficult to distinguish for a human also. This basically means that if you look at the kind of search side of the problem, that we can almost do perfect search with those systems. So if the things you're looking for are fixed, if your keyword that you're using fits any of those terms we have here, then your search index is in most cases sufficient to find what you are looking for. That is different if we start looking for exploration. So for exploration, you have different kind of methodologies, and you have different kinds of looking at your data. And if you're looking at the search exploration axis, and that's again from the paper that we were talking about, you can see that there are kind of different category-related tasks that are here. So the task that we are looking here, so ranking, well, basically is distinguishing the top part from the bottom part, which is important. Finding relevant items, finding needles in the haystack. It's basically a binary categorization problem, where you have to identify relevant items for the category and non-relevant items for the category. If you talk about structuring of your data, you start doing clustering and maybe giving your clusters a name, then you're also can view this as a category-based problem, but then your categories are not single. It's not a single category, but there are multiple categories. But for those two tasks, they're still usually fixed. So if we start into the browsing category, then you will have multiple categories which can actually dynamically change, because what the user is looking for can change. And also based on what you have found, you might reinterpret what you were looking for. So again, this is a more difficult part because it's dynamic, but all three, those three components, the three different types of categorizations basically can do all the tasks that we are looking at here. So they are a very convenient way to look at those different models that we have there. model tasks, sorry, that we have there. And by now, by doing very intelligent things, we can also do this in a very, very fast way. So this is work with, among others, Björn and Laurent. Omar is also part of the meeting, I saw. And what it is based on is a very compact representation of your data, where instead of the 10,000s of concepts that you have in ImageNet, you reduce it to the ones that are really important. So you only focus on a small subset for every image that are very important to describe that particular image. You do a similar thing for text. And with this very compact representation, you also have a way to generate a very efficient index. So we started with this representation and then added later a method to pre-cluster your data. And by using that pre-clustering of your data, you have a very efficient way of getting access to your visual and your textual features. So that has been made part of the acquisitor system, where the user is indicating the relevance of particular items, so whether they're positive or whether they are negative to what they are looking for. And based on that information, you train a classifier on the whole data set, where you try to find a best separation between the positive examples and the negative examples. So basically what you're doing is to create a new concept. You add a new concept to, in this case, ImageNet. You do that on the fly. So then you get your candidates, you fuse the different modalities, and then you give the result back to the user, and then the user can iteratively find new elements. And it's a little bit small on your screen, probably, well, also on mine. But the collection that you see here, the example that we have been working on, is the collection of YFCC, which is composed of 100 million images. And this process of judging relevance, well, after judging relevance, retraining your classifier and being able to present suggestions to the user is done within 0.3 seconds on 100 million items. So this is really, really fast, and that makes that we can do a lot of interactive processing and a lot of interaction rounds with the user. And we have built multiple systems along these lines of reasoning. One of them is the multimedia pivot tables, where the colors you see here are actually denoting category membership, and you see many different kind of summaries of your data. It contains geographic data, it contains textual data, it contains image data, and all kind of other channels that you can use and combine in one system. This is a very recent system that will be presented at the Visual Analytics Conference in a month from now, which is built on the Tetris metaphor, which you might know, this little game where blocks are coming down from the sky. You have to put them in the right place. So here it is a categorization system where black fawn is actually on the bottom here. An image comes in, and you put it by controlling where it goes with your keys. It goes into one of those little elements here. And by doing this multiple times, the system gets smarter and smarter and smarter. And in the end, it basically will flow every image to the right place. And only when it makes a mistake, you have to suggest that it should go to a different place. But these are all category-based. We'll move on to a different class of methods, the graph-based methods. Because if you look at what we have been doing with the categories, we have been describing all images basically by this part of our data, so as individual items. And similarity is only used in a way that you are doing classification, so you need a metric for in your deep learning system, but you're not explicitly looking at relations within your data. Of course, graphs do. They are a way where everything is either connected or not connected, and nothing in between those elements. And that's another way of looking at your data. So this is something we have looked at already for a long time ago, but still the ideas are very relevant to what we are doing, or what we will be doing, what I will be talking about today. So if you have a large data set and you make clusters, for example, within those data sets, you can start making paths through your cluster. So if you would be at one point in your cluster, what would be the next element that would be good to look at, would be important to consider. And this is what we call static threads through your data set. So they're static ones, but if you start exploring, you will come in a different situation where you have a query shot, or you have your current shot or your current image that you are looking at. And based on that, you can dynamically find what are my nearest neighbors in terms of visual similarity, in terms of semantic similarity, in terms of temporal similarity. So you can have different threads based on this dynamically changing query element on what path would be a good path to go through. So based on your similarity metric, you basically go through your nearest neighbors in your system. And by doing so, you can create multiple threads through your data. So from this element, you can move to visual similarity, temporal similarity, semantic similarity, or any other similarity measure that you would have defined on your data. And we have used this to build these kind of browsing systems, where indeed you have this query element in the middle. That's what you are currently looking at. And just by using your keyboard or any other interaction mechanism, you can choose in which direction you want to travel and where you want to see more data. And think of what we saw in the previous element. As soon as when you start moving in one of those directions, of course, this path will be the same, but your other paths that you're looking at will change depending on the new element that you have. So again, it's a dynamically changing set of data elements that you are looking at. So if I look at my search exploration axis again, but now viewed from the perspective of a graph, you see that there are kind of tasks are kind of find characteristic nodes and structures. Typically what you also do in social network analysis, find the hubs in the network, find the ones with many connections, those kind of elements. You can navigate through a static structure, so predefined structure in your data set, or you can be browsing along different dimensions through your data set. So again, what we have here are different representations that play a role. So here you're basically having the nodes and the edges and maybe some statistics on top of them. And for this part of the system, you have the threads. So linear paths through your data set. And they are very good for exploring your data set. But we go further than just the graph-based methods. We want to move to the next step, because there are a number of things that graphs actually cannot easily describe. So here you see a graph where we have different connections between elements, different types of connections, but you have text elements, you have users, you have images, and they also provide groups on top of your data. So having multimodal entities within one graph is difficult. I mean, there are ways of doing it. Of course, you can give every node a label, but then you need multiple labels for every node, for every dimension. It's not an easy thing to do. If you look at social media platforms, you talk about relations between people, but you're also talking about communities within this network. Well, how do you model communities within a graph-based method? That's very difficult to do. And same here, if you have kind of arbitrary combinations of elements of multiple dimensions, how would you incorporate that into one single representation? Something a graph in general also can't do is to take into account any context of the node of the element that you are looking at. So this is a example from an earlier paper by Johnson and Macaulay, where this is a picture of an element, and you could be wondering, what are we actually looking at? It could be different things. It might be a flower petal. It could also be a piece of fruit. It could even be an octopus tentacle, although if you're carefully looking, you probably see that it's not an octopus tentacle. But it's very difficult to determine what we are actually looking at. But now, if you would have a description where you know other elements in your neighborhood, which are annotated with the same tag, or who are posted by the same user at the same time, or taken from the same location, or submitted to the same group in a social media platform, you probably would be able to identify that this is actually part of a picture showing a flower, because it gives you give more information on what we are actually looking at. So if you are able to leverage your contextual data, you might get better results to start with. So that's a good way of looking at your problem. So how do we go from graphs to hypergraphs? So in a regular graph, well, I don't have to explain you, of course, there's an edge is just a connection between two vertices. So hypergraphs take that idea one step further and say, well, an edge can be a connection between any number of vertices. Why did we choose earlier to always say it can only be a connection between two elements? Why not more? So we can have an edge which only contains one single element. We can have a edge which contains three elements. We can also have another one with three elements, where one of the elements actually comes back in two of the edges. And it could also be the whole collection that we are looking at. So hypergraphs are a much richer way of describing our relations. So not only the relations, but also the groups within our data. And there's a long history already of using hypergraphs and working with hypergraphs. So the idea of having a hypergraph was already in 1973. That was Birch was the first one who came up with the idea that you can actually consider multiple edges rather than only single elements in an edge. And in 2005, so quite some time later, someone came up with the idea, Gori and al came up with the idea that you can use this idea of a graph and do graph neural networks. So having a simple neural network to learn how hyper edges are connected and what they are representing. And then, of course, in 2012, we already talked about it. AlexNet came into being, and ImageNet before that, and the age of deep learning started. And that also changed how we were looking at graph-based analysis within the kind of context people were talking about here. And in 2014, Bruna and all, they came up with a kind of signal processing way of looking at hypergraphs or analyzing hypergraphs. And that was the first part where they combined elements from signal processing with matrix analysis and used that in a deep learning context. So they brought it to the next kind of level of analysis. And then in 2017, Thomas Keith and Max Welling from our institute, they came with an approach where they really made graph convolutional networks feasible by using a semi-supervised learning approach, so that they were not using all the data when they were retraining the network, but they were using part and leveraged information around it to be able to learn in a very quick, in a more efficient manner, new representations of the graph. And we took that idea a bit further, and that's what I will be talking about now. In 2018, at ICMR, Devanshu and I wrote a paper on doing similar things, but then in a hypergraph context. So the idea of a hypergraph, the idea of a graph convolutional network is basically very similar to what you are doing within a convolutional network, the standard way of analyzing image data by now. But instead of having a pixel and having a square region around it to do convolutions, the neighborhood in which you do your processing is not a small square within your image, but they are just the neighbors within your network. So in the hidden layers that you now have in your network, you're aggregating data from your different neighbors, and then you pass through a nonlinear function to go to the next layer, and they do similar things, but now of course you're integrating over larger regions. You do another nonlinear output, and you get to an output function in which you are analyzing, in which you give your final result. But that's the basic idea. Most important thing is that you're aggregating data from your neighbors. So for the hypergraph extension to this, looking at how to deal with that, what you do, you first have to represent the hypergraph itself, and you do so with an incidence matrix. So you're, say, for every node that you have, to which of the edges it belongs. So clearly, if you were looking at a simple graph, a regular graph, every line here would only contain one element. So only one non-zero. For an hyperedge, it could be anything from 0 to all elements being 1. So that's the matrix with which you start your analysis, and with which you start your reasoning with your data and learning of your representations. And what we aim to do with hypergraphs within this method of doing analysis is, if you have an image, if you have an item with a lot of relations connected to it, which could be based on labels, so other elements with the same label, or images from the same user, or this image is part of a group, and what are the other members in the group, which pictures have the same tag as this one. So all those kind of relations that you can have for a particular image. And what we aim to do is to take some of those. So you take one of those elements, keep that as a fixed relation between your items, and then use that to say something. So those are the explicit relations between the entities, and use the explicit relations and the implicit relations you already have to find more implicit relations, or sorry, the relations that you already have here, find more implicit relations in the network. So you use one type of information to infer very interesting elements of your other relations that you have. And the way you formulate it, or it is often formulated, is as a matrix completion problem. So we had this matrix, So we had this matrix, which ones are connected, and some of those elements are filled. So those are the elements we already know that they are having a relation in this particular dimension. And the question is whether you can add additional elements to this matrix based on the information that you have in the other matrix, in the explicit relation matrix. So you're trying to find new implicit relations within this matrix, and that's why it's called matrix completion. And what you typically do, so this of course is a very high dimensional matrix. You try to reduce it to a lower dimensional matrix in which most of the information is preserved, but still reducing it in the, preserving most of the information, but also the way it is given, it's a very sparse matrix. So because it's sparse, it will also be a low rank matrix. So it also makes sense to go to a lower dimensional matrix than you originally had. And what you then have is that you create a matrix, a large matrix of the combination of, in this case, as an example, you have a graph of movies and you have a graph of users. So you combine them into one matrix just by taking their multiplication, the one in transpose. This is what original methods did. So they started with making this matrix and then started doing the analysis. We'll come back whether that's a good idea or not. It can be probably improved. So what then came were the so-called multi-graph convolutional networks. So they work on the following principle. If you have a matrix like this, you can kind of view it as an image. It's similar to what you would have as an image, because you have, at every entry, you have a value, and it is a square set of what you could call pixels. And it turns out that similar kind of things that you are doing for images, namely filtering, you can also do on images like this, so on matrices. So you can do a kind of similar thing as a Fourier transform, but then on the matrix. And the nice part about the standard Fourier transform, and the same thing can be done here, is that you can decompose a Fourier transform in a horizontal path and a vertical path. So you can decompose the two dimensions to be more efficient. Of course, a matrix and an image are not the same, so you're doing it in a slightly different way, but the idea is similar. So what we are, as I said, what we are trying to do is to have a set of explicit relations. So things where we say, okay, these are true elements. This is what we are indeed, that we already know, and that basically we're not going to change during the course of our analysis. And at the same time, we have another graph where we have already relations between different elements. So in this case, they are grouped. So the hypergraph is built by grouping images that have the same tag. So those are all tagged with fun. Those are all tagged with bike. And we want to take those two inputs. We want to work with those two matrices, build a model from it, and do an hypergraph update here. So it's continuous change till we have a optimal model. And in the end, we should have things like this. So in this case, you have new categories, new connections between different elements that we didn't have in this original matrix. And that's the goal of doing this hypergraph representation learning to be able to find those kind of relations. So what's the overall system look like? So we have these implicit relations between our elements, which we want to extend with new implicit relations that we haven't found yet. So we have a partial hypergraph, a partial incidence matrix with the ones that we already know. That we already know. Oh, sorry. So the relations that some of them we already know, some of them we are trying to find. And we have this set of explicit relations that we keep fixed. So that's the complete hypergraph on our data. And for this part, we compute the so-called population matrix, which is a way of kind of taking the most important information out of your data. So you can make a decomposition into different, in a number of components, which makes it easier to do your processing. This is the part that deals with the, we'll do first this part, sorry. You have the incidence matrix, and here you basically do your matrix factorization. So if this was users and movies, you try to bring it back to movies and users again. So the columns, the rows separate from the columns, and multiply, they will give this. But in practice, you can actually work with this part. I mean, it's an approximation. It's not perfect, but of course, it saves you the continuous matrix factorization that otherwise you would do. Well, combining these with this part, you can do the feature extraction using those graph convolutional networks with higher order multimodal data. So here is where the network is the part that Keith and Welling have been doing. They combine this information and that information, and they try to optimize this loss function. And this loss function, what it does is, on the one hand, try to make a well enough lower ranked set of data, but still taking take the lower rank in your of your matrix. On the other hand, also take into account that you might have some noise in your data. So you want to find a balance between being robust against noise and having a very low dimensional representation. Well, you cannot do this in one go. It's not a deterministic algorithm. And what you do is you're making time steps where you make small changes to your relations in your hypergraph, and you do so with a recurrent neural network. So your recurrent neural network makes different time steps, and your network here has some memory of the previous steps, and from there you build up the final model that you have here. So that's the basic method we are using for creating hypergraphs and to predict new elements, new relations within our hypergraph. And we aimed to do interactive exploration. So how do we interact with this? Well, the user will see this result in some visualization, and then the user can interactively either change nodes, remove nodes, add nodes, or say that this element should probably not be part of city life. So basically taking this up there. The visualization will of course look different, but you remove element from a hyper edge, you combine hyper edges. But this is the kind of interaction that a user is doing. Oh. And based on this, you update your incidence matrix. So you update the nodes and the affected hyper edges. Of course, in practice, you will do so already via this matrix factorization. But so if you remove a node, of course, you also have to remove all edges that are connected to it, all elements that have a relation to this one. So you update your matrix, and then you retrain the model. So you take new steps here, but instead of doing the full process of learning, you only retrain the final step in your model. You only do a number of iterations, or you start with your current model and you do a number of additional steps. And by doing this, you kind of create a ripple effect through your whole data set. So not only the elements that you have here are affected, but you also see changes to elements that are connected to the connected elements. So you slowly see information going from one place to the other. So it creates more than only a change in the individual matrices that you have here. So really you see changes happening here in your hypergraph, which go beyond what the user has been doing. So it really learns how to propagate that kind of information. So this is an example thing that we have been working on as a use case in conjunction with law enforcement agencies. So we look at Stormfront, which is a violent political extremism internet forum, where you have images, you have text, so you have posts that are made. It's done by a particular user. It has some text associated with it. It has images associated with it. It has avatars. It has a forum category. It has national networks. So it has a lot of multimodal data to look at, and we bring that into textual entities and visual. We use text entities and visual concept detection, and we have the relations that are already in there. And we try to find new relations, new topics that people are talking about within the network. At least they are not talking about it yet, but they might be talking about it in the future. And that is, of course, what law enforcement want to see. Are there some extremist texts being created? Is someone radicalizing within this framework? Those are the kind of things that we try to estimate using those new relations. And we do so with interactive visualizations, and the visualization part is mostly done in the University of Constance, the top in visual analytics. And when an investigator is analyzing this kind of data, it will first look at interesting connections. Well, there are a lot of interesting connections to look at. Then it might look at how those connections are changing over time, how much is it changing, where are kind of interesting things happening. Then it might look at conversations between different people in different fora. And only then, in the end, it will look at the individual content elements of the piece of text that has been addressed by this particular person. So you see that you go from a lot of data, so they're typically in the in this case, 256,000 range, to kind of 60,000. In the end, you only have a few number of elements to look at. This is our full exploration system, where here you have the set of users. Here you have the set of different topics, and it's a fixed set of topics, and you see supremacy, racial realism, anti-German sentiment. I mean, those are the kind of things they talk about in Stormfront. And this is the user topic matrix. So this is how well a user is connected to a certain topic. So the brighter the value here, the more this user is actually writing within this concept. And the ones that you're seeing here in dark blue, those are the ones that have been talking in that topic. And light ones might be the ones where we expect them to be writing on the topic. So seeing this visualization and having read what is in this text, an expert might decide that although the system says that this is about a certain topic, it may be not about that topic, or when it doesn't identify this as a topic for this one, it might actually be relevant for that topic. So the user is changing things, and based on the change, this element will change. But as I said, you make this change, but based on this change, it will also make changes to other parts of your visualization. So it's a continuous model of updating. So in conclusion, we had the search exploration axis as our way of looking at the different tasks that we have within our system, and we have categorization as a way to describe those different tasks, or a way to interact, to create methods for them, where these are the elements that you change and your basically your data model that you work with. We looked at a similar thing for graphs, where we have nodes and edges as a representation and threads as a representation. The nodes and edges more on the search side, the threads on the exploration side. But now let's have a look at the global picture. So we have a search exploration axis based on categories, and we have another search exploration axis based on nodes and threads. And now if we look at the hypergraphs, so hypergraphs are basically having nodes and edges, where the edges can be having multiple elements. And if you make a linear set of elements, it becomes a thread. If you have a group of elements as a hyper edge in your data, you're basically talking about different categories. So the hypergraphs kind of bring those things together. And I'm not saying that we already have the answer of how these are connected, but it's an interesting way to look at what is happening in the search exploration axis. And with that, I would like to thank you for your attention. I couldn't see your faces, or I couldn't see what people were doing, but I hope you enjoyed the talk.